Hello, my name is Julia Fleischman and welcome to my Lab 4 report. Today we will go over the introduction and purpose of this lab, summarize our findings from both our experimental and computational models, compare the two, and answer any remaining questions at the end. Our purpose today is to observe the motion of a spring mass system in which the mass swings in an arc while oscillating on a spring. We'll do this by creating an experiment through Tracker, model the experiment through code, and compare the graphs. But before we get started, we must go over the fundamentals. Newton's second law can then be transformed into dp dt equals F net, which equals delta P over delta T, with P representing momentum and T time. We then have our velocity and position update formulas, which are in order V final equals V initial plus F net divided by M times T, and R final equals R initial plus Vt. We must also use the simple harmonic motion equation, which is 2 pi square root times m divided by k, with m representing the mass of the object and k the stiffness of the spring. We then also have the force of gravity in vector form, which is 0, negative mg0. The spring force, which is negative k s l hat. S equals magnitude of L minus L naught. The energy principle delta E equals W plus Q, the kinetic energy formula 1/2 mv squared, and the universal gravitational potential energy formula, which is UG equals mgh. Some other things to know is to recognize our system, which includes the mass, earth, and spring. And for the purpose of this lab, we will say that there's nothing in the surroundings to make calculations more simple, when in reality there are drag forces and other forces of friction acting upon the system. Our initial position is negative 0.111, negative 0.640 meters, and our final result is that the oscillation of our object follows the energy principle. I inputted a video into Tracker and plotted its motion over time. As time progresses, you can see the graphs of the x and y positions of the object start to develop into sine and cosine graphs. I then used the data gathered from Tracker to calculate K and L naught, which turned out to be 6.878 newtons per meter and 0.127 meters, respectively. In our computational model, we inputted the mass as 0.402 kilograms and initial position of negative 0.111, negative 0.640 meters. I then filled in our gravitational constant G as 9.8 meters per second, K as 6.878, and L naught as 0.127, which we obtained from calculations shown in the previous slide. I then inputted the kinetic energy, gravitational potential energy, spring potential energy, and total energy formulas into the code. Then, later on in the code, I inputted the spring force and both update formulas in their respective position. Finally, here we are just calculating all of our changes in kinetic, gravitational potential, and total energies. As for our results, we can see here that the orange line represents delta E, or the energy principle, which remains at 0 for the entirety of the experiment. As for the two graphs on the right, the model closely predicted the x position, but not as much for the y position. This could be due to our experimental model experiencing drag forces that our computational model did not account for. Some potential sources of error are that we did not account for other forces acting upon our system, such as drag forces or other sources of friction. We also considered only one type of energy, when we could have also included rotational kinetic energy and thermal energy. Finally, we have to take into account of natural human error. When I tracked the center of the mass of the object, I did not consistently always record the same center of mass. Now we move on to further understanding. In our model, is the energy principle satisfied? Yes. The orange line that represents the energy principle stays at a constant 0 throughout the graph. What are the differences between the oscillation periods between the x and y graphs? The x position oscillation period is longer because the forces acting upon the x position have smaller effect than those in the y direction. Thank you so much for watching.